Hello, I'm Mr. Muskeluk, your AP Chemistry teacher at ChemAdvantage.
Well, here we've got a problem that has stoichiometry, limiting reactants, and percent yield, and also some pretty interesting chemistry. This is focused on titanium, which is just an amazing metal. Low density, very high melting temperature. It's very strong, but it's also very difficult to work with and also difficult to make. Be sure to watch the video on how titanium is produced that I've got on the description. All right, here we go. Let's look at the problem. Titanium is a difficult metal to purify from its ores. Okay, it's prepared by a reaction of titanium-4 chloride. Well, titanium's interesting, and so is titanium-4 chloride. That's its official name, but most people don't call it that. It's usually called titanium tetrachloride, which is probably a better name because even though titanium Roman numeral 4 chloride would be correct if this were an ionic compound, which you'd expect because you have a metal and a nonmetal. But look, it's a liquid at room temperature, so it's really a molecular substance and doesn't really deserve a ionic name. Hence titanium tetrachloride, or as they sometimes call it, TiCl. On contact with humid air with some water, it reacts and produces titanium dioxide, this magnificent white pigment in such fine powder that it produces a smoke cloud. And in fact, it was used to produce smoke clouds in military operations. And here's a little video that shows this reaction. It's done by ChemForce, and ChemForce has a lot of neat videos that you might want to watch too. I've got its address also in the description. All right, titanium tetrachloride, a liquid, and let's get back to our reaction. Reacts with magnesium. They put these two together in these huge vessels, heat the heck out of it, just an amazing production. And then they get this titanium sponge, which they then process to make these beautiful sheets of titanium that have all these special uses because it has such a low density and high melting temperature and strength. Well, let's get to the problem. The reaction between 69 grams of titanium tetrachloride, or TiCl, and 13.8 grams of magnesium produced 9.66 grams of titanium metal. Well, they've got three numbers here to deal with. A limiting reactant problem has more than one reactant. And this is the giveaway. They say, okay, we've got some titanium chloride. Normally, you just go and do stoichiometry and figure out what's going to happen. But they also give you the other reactant. So you have to say, which reactant am I going to use? And that's the first part of a limiting reactant problem. We'll come up with this product later on when we do our percent yield. Because when they tell you how much you make, then you have to deal with percent yield too, which I think is easier than limiting reactants. So let's work on this problem. Let's start with the first thing. Well, no, the first thing is the equation. They gave us the balanced equation. This would have been an easy one to balance. And when they give you a balanced equation, I'd write it out and then realize that we're going to deal with a mass. We're going to have to deal with atomic masses, and we'll have to deal with moles. And I always put the moles up here because the moles are going to follow the coefficients of our balanced reaction. So I've got my balanced equation. I put down my three rows, my mass that I use the data with, and then my molar masses, which I can find using the periodic table, and then moles that are supposed to follow this stoichiometry. So let's take the first substance here, titanium TiCl chloride, 69.0 grams, and we've got that mass. Now the titanium tetrachloride is going to have a molar mass that includes titanium and 4 chlorines. So calculator time, I'll pull that out and find out that molar mass. Here's my calculator. So titanium tetrachloride, let me see. We've got one titanium, which is a 47.87, and we're going to add to it our chlorine atoms, 35.5. I didn't bother to look that up because I remember it. We use chlorine so often. Of course, times 4. And we'll get our answer. I'm going to write that down right here. There it is, exactly what we expect. Now we're going to have to change into moles. So I'll take my 69 grams, and by now you really, really should know how to change grams into moles without having to do anything else. And know that you can use your calculator's answer to find an answer. And also realize that you're not going to need all of these numbers. Save yourself some time. And there's our 0.363. And that's right. We have about 70, we have 120. We'd expect a fraction. Now, normally we would just go through and do our stoichiometry thing, but this question has 13.8 grams of magnesium. It's got our other reactant there, and we're going to have to deal with that 13.8 and change it into moles too, and then do a little trick to find out what's happening. I'm going to take my 13.8 and divide that by my 24.3. Magnesium, this light flammable metal, not nearly as strong as titanium. There's our answer, 0.568. Let's see if we had that right in that. There's our 0.568. So which one of these two are we going to use for the rest of our stoichiometry? Because we want to find out how much titanium is made. You have to find out which of these things you have the least of. That's going to be your controlling factor. This reaction is going to go on until you run out of one of the reactants, and then it's going to stop. You need both reactants for this to occur. As soon as you run out of one, the other one's saying, hey, I've got nothing to react with. This magnesium, two magnesiums, have got to react with one titanium. Looks like we've got plenty of magnesiums here, 0.568. So you say, hey, I'm not going to run out of magnesium, but this is a 1 to 2 reaction. You're going to need twice as much magnesium as titanium tetrachloride. And you can see here, if you need twice as much, we don't have quite that amount. Now, sometimes it could be not quite as obvious as to which substance you're going to run out of. So here's the general rule. If you can't quite see what's happening, you look at both reactants. Okay, here's our 0.363. And divide by the coefficient it has. Well, there's a 1 here, so don't have to do much division. 0.363. Here we have a coefficient of 2. So I'm going to take this and divide it by 2. I'm going to take my 0.568, divide it by 2, and I get a 0.284. 0.284, the reduced version. Once it's been divided by its coefficients, you can then compare. You say 0.284 is less than 0.363, and therefore the magnesium is our limiting reactant. That's what we're going to use for our stoichiometry. As I said, you could have seen this saying, hey, I need 363 titanium tetrachloride. I'll need twice as much. I don't have it. Or you could use this technique, divide by the coefficients, and see which you're short on. That will tell you. That's a nice, fast, reliable method. It's a trick worth remembering. So we know magnesium is going to be our limiting reactant, and that is what's going to rule our reaction. I'm going to go back and multiply by 2 again to see that original amount is back. Now we're going to be making, what are we going to make? Titanium. To find out how much titanium is going to be made, we will have to use our magnesium, not our titanium chloride. This is what we've got too much of. You have this in excess. So the magnesium rule, because that's going to determine the amount of titanium, and the magnesium chloride, our extra little product that we don't care about right now. We know how to go from 1 mole to another. You divide by your coefficient and dividing by 2 again. And then we multiply by the new coefficient. And our new coefficient is going to be a 1. And this makes sense. We're going to have 0.284 moles of titanium. That makes sense. I see 0.568. I'm going to need 2 to 1 ratio. I'm not going to get as much titanium in terms of moles. It takes 2 magnesium. This is expensive for magnesium. And only get 1 titanium. Well, let's get to our mass, because this is what's determined. My titanium tetrachloride, that is in excess. In fact, actually, I'd only be using 0.284 moles of titanium tetrachloride. So we're going to find our mass, calculator, pull that thing out again, and go times the molar mass of titanium, 47.87 grams per mole. You know how to change moles into grams. Here's our mole row. We multiply down here, and we'll get our grams of titanium. So you could have 69 grams of titanium tetrachloride, You could have 13 grams of magnesium, but you're only going to make 13.6 grams of titanium. You're sort of wasting your titanium tetrachloride liquid that you made here. It'll evaporate away. But you don't want to have extra magnesium left in your container. That's a contaminant. It's a metal, and you don't want it to mix with the titanium. Your titanium alloy is going to be all messed up, so you're better off having an excess of titanium tetrachloride. So we've answered our problem. What mass of titanium could possibly be produced from these amounts of reactants? Limiting reactant problem. That's great. Be sure you can work on these and know that little trick of dividing by the coefficients to find the limiting reactant and use that limiting reactant in your stoichiometry. Well, let's go on to our next part of the problem, because I promise you percent yield. In this reaction, after they sealed all this stuff up, heat the heck out of it, and then chop it up and remelt it, they only get 9.66 grams of this beautiful titanium. Of course, this is smaller than we expected. We expected to get 13.6. What's the percent yield? Well, there's a simple formula for percent yield. It's a logical one. Percent yield tells you how much you actually got compared to what you theoretically should have gotten. You know, in chemistry, we can figure out theoretically how much could be made. That's what all these numbers are for. That's what we learn moles for, and atomic weights. You take your experimental, what you got, 9.66. Divide it by what you theoretically could have gotten. We calculated this, 13.6, and then multiply by 100. I've got my 13.6 still in my calculator. I'm going to realize I had 9.66 divided by my answer. I could have typed that in, but I could make a mistake and transpose numbers and forget a decimal point. And then I'll multiply it by 100. That's a waste of time. I could have moved the decimal point. And we have our 71, and forget all these extra numbers. 3 significant digits. Let's see. 71%. So we could have gotten 13.6 grams, but we only got 71% of that. So we've done limiting reactant, stoichiometry, and percent yield. You're an expert chemist if you can do this sort of thing. And please watch that video on how to make titanium.